Welcome to this video. My name is Mark Scythian. The date today is March 3rd, 2024. The title of this video lecture is Potential and Kinetic Energy Concepts, Fundamentals, and Applications. So to skip through the contents a little faster here, we have a table of contents including the common scenarios where potential and kinetic energy can be demonstrated practically. So if we just skip through the introduction, we will cover the slingshot, ballistic device, i.e. firearm, suspended object drop from a given height, compressed, spring, released, and then the cart rolling downhill. So if we go back to the introduction here, there's a few fundamental points to make. So the whole concept of energy itself is the capacity to perform work. And this is broken down into either the energy at rest, potential energy, or the energy in motion, kinetic energy. We cannot create or destroy energy. We can only change its form. So this is the law of conservation of energy. This is also known as the first law of thermodynamics, the conservation of energy. So a system with a given potential energy that discharges into kinetic energy has not created or destroyed any energy, but has only changed its form. So there's all sorts of energy conversion going on with machines and devices in any system. So we have some total input power, some of it absorbed to power that device, and then whatever's left is available power for practical application. So case in point, like combustion engines, they're going to extract about 60 to 80% or 60 to 70% just to run the engine, and then whatever's left is usable power. So that is a conversion of potential energy in the fuel, the chemical potential energy, into kinetic thermal energy through combustion. And so through that process, there is neither creation or destruction of energy and matter, but only changing its form. So obviously the spent combustion charge, the air and fuel charge in a combustion engine are leaving the engine as the exhaust gas flow or the mass airflow out of the exhaust. So we have not created or destroyed any material nor energy, but we've only changed its form. So if we back up a bit to some larger fundamentals, such as the conservation of energy itself, then we can narrow it down to potential and kinetic energy. These two are equal to each other in a system. So we have different types of potential energy, such as the elastic potential energy charged into a rubber band or a bow and arrows bow or a slingshot sling, etc. And by exerting that draw, let's say on a slingshot sling, there's a certain force exerted times the distance of the draw. So if we multiply these two values out, and let's say pounds times feet, we've now calculated a foot-pounds of potential energy value. So when we release that bow or that sling, the string or the sling for a bow and arrow or a slingshot, we then convert the potential energy into kinetic energy in equality. So if we measured a potential energy of, let's say, 10 foot-pounds, we're also going to get 10 foot-pounds of kinetic energy. So if you get one or the other, you're able to make it equal to the others equation. So again, if we have a resting object suspended above a certain elevation, like a floor, for instance, we have a mass times the gravitational acceleration, so the weight, times the height. So the W times the H, the height. So we then have also foot-pounds. And so the metric equivalent of foot-pounds is a Newton meter. So there is 4.45 newtons of force to 1 pound of force, and there's 0.45 kilograms of mass to 1 pound of mass. So that's the relationship between the metric and US equivalency. Again, for distance, we have 0.305 meters for 1 foot of distance. So if we were to find the conversion factor between foot-pounds and Newton meters, that is 1 foot-pound is equal to 1.36 Newton meters. Newton meters are commonly referred to as joules. This is not the same as joules per second, because a joule per second is 1 watt of power, but just a joule by itself is a measurement of work. Force times distance, in this case, a Newton meter is a joule. However, 1 foot-pound is 1.36 joules. So that's the conversion. So if we wanted to go the other way, we could divide 1 over 1.36 Newton meters and compute 0.737 foot-pounds to 1 Newton meter, either or. And so if we reduce down the values of kinetic energy, you can usually tell the formula of a system based on its units. So if we go down to the bottom here, we have 2 common potential energies: mass times gravity, the weight of an object times the height. And this is for gravitational potential energy. And then we have the elastic potential energy, the force times the distance incurred into some material with elasticity. It's pounds, force, and tension times the draw, length, and distance. So this could be made equal to kinetic energy, which is always 1/2 mass times velocity squared. So if you know the mass and you figured out the potential energy, you can easily solve for the velocity of the item that will accelerate after converting the potential to kinetic energy. So a good example is releasing the bow and arrow, or the slingshot band, the bow and arrow string, etc. So that's just the basic overview of the introduction to fundamentals, but really the understanding comes when working with practical applications. So in this case, we have a slingshot with a sling band for which 10 pounds force of stretching force is applied to a 1 ounce rock, and the actual draw length, or the stretching length, is 14 inches. So we can convert the 14 inches into feet, 12 inches to a foot, and then convert the feet into meters, 3.28 feet to a meter. So 0.36 meters is 14 inches. And we convert the 10 pounds of force into newtons, and 10 times 4.45 is 44.5 newtons. And then there is 16 ounces of mass to 1 pound of mass as well. And so this is not volume ounces, this is mass ounces. 1 ounce rock is hence 1/16 of a pound mass. So that is the value of 1 divided into 16, or 0.0625 pounds mass rock, divided into 2.2, the number of pounds mass to a kilogram, and the rock has a mass of 0.0284 kilograms. So the potential energy of the slingshot, sling and draw 14 inches and 10 pound of force is equal to either 10 pounds of force times 1.17 feet, 11.7 foot-pounds of potential energy, or 16 joules, 44.5 times 0.36 newtons times meters. So after the rock is released, its total kinetic energy before impact is equal to its potential energy, hence the conservation of energy. So what is the rock's release velocity? So after we let go of this rock, what is the velocity? So we could take the F times D and make it equal to 1/2 mass times velocity squared. PE is equal to KE. 16 joules is equal to 1/2 the mass, or 0.0284 kilograms. So this then becomes just 16 is equal to 1/2 of the mass, 0.0142 times V squared. So we can then solve for V squared by dividing the 0.0142 into 16 right here. And then to get V, we can get the square root of the other side, because the square root of V squared is V. So what we do to one side, we do to the other side. So the velocity is the square root of 16 divided into 1/2 the mass. And so we compute 33.6 meters per second. We can convert back to feet per second. 33.6 meters per second times 3.28 feet per second to meters per second. So we get 110.2 feet per second. So based on the draw and the mass and the force involved of extending or stretching the sling, we get a rock accelerating from rest to 110.2 feet per second. So the distance divided by the time squared would be the acceleration, but that's more for kinematics. But this is just covering the broad concept of potential and kinetic energy. So here is the next example. So here we have a certain length of barrel, which could fall more into kinematic. So we can just take the specs of the ammunition here. So 1120 feet per second, that's the velocity of the kinetic energy curve. So we got to convert this 116 grain into kilograms. So 64.8 milligrams to a grain divided by 1,000 to get grams, 454 grams to a pound, divided into 2.2. So we have 0.00754 kilogram projectile, and then we convert the feet per second to meters per second. Then we use the 1/2 mv squared to compute the potential, or the kinetic energy, in this case in joules. So 0.5 times the mass of the round times its velocity squared. We compute 437 joules. We can divide this into 1.36, so it's 321.3 foot-pounds of kinetic energy. And then we can look up the energy density of smokeless gunpowder, 3504 joules per gram. And of course, we could do the ratiometric conversion, so 437 into 30504 times 1 gram. So it'll take a minimum of 0.12 grams of smokeless powder in potential energy. We multiply this times 1,000 divided by 64.8 milligrams per grain. So it's approximately 2 grains of smokeless gunpowder. Of course, there's going to be a little bit more to overcome the friction and the lands and grooves, and as well as the vacuum trajectory losses, etc. So they're usually like about 3 or 4 grains, but for actually accelerating the bullet, ignoring efficiency losses, it's a minimum of 2 grains. So that is potential to kinetic energy example. So another one, we have gravitational potential energy. We can take mgh, the weight of the object, so 10 pounds into 2.2 pounds per kilogram to get the kilograms mass times the gravitational acceleration on Earth, 9.81 meters per second squared. So that will compute the Newton's force, weight of the object times the height of 30 feet, so 30 into 3.28 That's the meters. So we compute 407.8 joules. And if we want to convert that back to foot-pounds, it's 299.8 foot-pounds. So all we have to do is make this equal to kinetic energy. Substitute the M, solve for V. So this becomes 13.4 meters per second will be the velocity of the object immediately before it strikes the ground. So again, we can use this with springs. We can figure out the force to compress the spring times the distance traveled. We can convert it either to foot-pounds or joules. So in this case, we have 5.65 joules is 10 pounds of force to compress a spring, displacing the spring from uncompressed to compressed by 5 inches. 5 inches becomes 0.416 feet or 0.127 meters. So out of this, we can compute the force times distance, potential energy, to get foot-pounds or Newton meters / joules. And so then if we were to release this release the spring with a 0.25 pound object, we could then make this equal to the potential energy, 5.65 joules made equal to 1/2 mv squared. We place the 0.52 pound object in for m, 1/2 the mass. This divided, or the 5.65 divided into 0.5, half the mass value. That equates to the v squared is equal to this ratio here. And again, just like on the first view, the slingshot example, we then have the velocity computed at about 10 meters per second or 33 feet per second. And so the energy is conserved. That means the potential energy cannot be created or destroyed. It can only be converted, in this case, after the spring is released into kinetic energy in equality. So it's an example of finding one to figure out the other, either potential or kinetic energy. And lastly, these problems, I guess it tends to annoy some students about the actual final velocity when the cart comes back down to ground level, but it's really simple. You have to find the height function. So forget about the rise and run and everything else. It's about the descent from 25 feet to 0. So this cart's at rest, not moving. It's about right at the point to where the gravity vector is not perfectly straight. So it's going to start making an angle and then pulling the cart down. And so we can ignore the rolling resistance, friction, and all that. We can it's very, very negligible once everything starts to speed up. So what is really relevant is the drop in altitude. So m, the mass of the car, g, the gravitational acceleration, 9.81 meters per second squared, times h, height, in meters. So we just take 25 and the 3.28. So the potential energy is 1359.5 joules. And again, if you want to convert that into foot-pounds, you just divide it by 1.36. So 999.6 foot-pounds is the potential energy. We make that equal to 1/2 mv squared. And we replace the m with the 40 divided into 2.2. And so this then allows us to solve for v squared and ultimately v. So the cart right when it reaches 0 altitude, right at this point, it will attain a final velocity of 12.2 meters per second or 40 feet per second. And of course, after rolling at 0 feet ground level, it'll start to lose speed as the rolling resistance opposes the inertia and slows it down. But it's really when the cart immediately reaches 0, that is when all the potential energy has converted into the maximum kinetic energy. So we have the final velocity. So it's all about the conservation of energy and finding one to solve for the other. So thank you for watching this video and have a great day.